If you zoom in on a glass of water, you'll find billions of molecules moving randomly. But thermodynamics completely ignores that microscopic view. It is a macroscopic science, meaning it studies the bulk properties of matter, like the water in that glass as a whole, rather than the individual atoms inside it. For a long time, scientists thought heat was an invisible fluid called caloric that flowed from hot objects to cold ones. That idea held until 1798, when Count Rumford noticed that boring out brass cannons generated enough heat to boil water. The friction from the work created the heat. Since a dull drill produced more heat than a sharp one, a fixed caloric fluid couldn't be the answer. Heat is actually a form of energy. This creates a clear dividing line in physics. Mechanics measures how a body moves as a complete unit, like a bullet flying through the air. Thermodynamics measures the internal, disordered state of that body, like the bullet heating up after it strikes a piece of wood. To describe that internal state, we use state variables. These are macroscopic measurements that define a system in equilibrium, including its pressure, volume, mass, and temperature. You know that rubbing your hands together in the winter makes them feel warmer, but relying on human sensation is subjective. Physics requires a rigorous mathematical framework to define these state variables so they can be accurately measured. That precision begins with a concept called thermodynamic equilibrium. A system reaches equilibrium when its macroscopic variables, like pressure and volume, stabilize and no longer change over time. Whether a system actually reaches that stable state depends entirely on the physical boundaries or walls that separate it from its surroundings. First, consider an adiabatic wall. An adiabatic wall is a perfect insulator that completely blocks the flow of heat. If we place two chambers of gas next to each other with an adiabatic wall between them, they cannot exchange energy. Their internal pressures and volumes fluctuate independently. Now replace that insulator with a diathermic wall. A diathermic wall is a conducting barrier that permits energy to flow from one side to the other. Placed next to each other, the two gases will spontaneously exchange energy. Eventually, that exchange slows down and stops. The state variables of both gases stabilize. When there is no more energy flowing across that diathermic boundary, the two systems have achieved thermal equilibrium. This stability points to a specific logical requirement. If two different systems can balance out like this, they must share some underlying physical property that has equalized between them. To prove this consistency, we can set up a strict three-body logical test. Imagine three distinct systems, A, B, and C. We isolate system A and system B from each other using an adiabatic wall. Then we place a conducting diathermic wall connecting both of them independently to system C. Because they are connected to C, energy flows. System A exchanges heat until it reaches thermal equilibrium with system C. Completely independently, system B also exchanges heat until it settles into equilibrium with system C. Now we execute the swap. We lock system C behind an adiabatic wall, completely isolating it. At the exact same time, we replace the barrier between A and B with a conducting diathermic wall. We watch for energy to flow between A and B, but nothing happens. Their macroscopic variables do not alter at all. Because they were both independently balanced with C, they are already in thermal equilibrium. This observation forms the basis of a strict physical rule. As the textbook states, two systems in thermal equilibrium with a third system separately are in thermal equilibrium with each other. It is a perfect transitive property. If the value for A equals C and the value for B equals C, then A must equal B. That shared equalized value finally gives us our rigorous definition. The physical quantity that is identical across all systems in thermal equilibrium is temperature. The practical application of this logic is immediate. By acting as the shared reference point for systems A and B, system C is functioning exactly like a thermometer. This is a vintage thermometer. Instead of relying on how a room feels, we let the mercury inside the glass expand to reach equilibrium with the air. By assigning numerical values to the height of that mercury, we construct a standardized temperature scale. Interestingly, the British physicist R.H. Fowler formalized this principle in 1931. By that time, the first and second laws of thermodynamics had been widely accepted and numbered for decades. However, physicists realized that this new rule was the logical prerequisite for everything else. You cannot govern heat and work transfer without first proving that temperature is a measurable, consistent state variable. So it was placed at the very beginning of the list and named the Zeroth Law. Today, when scientists measure the macroscopic properties of bulk systems in a laboratory, they rely entirely on that shared baseline to verify their work. The Zeroth Law extracts the concept of hotness from the realm of human sensation, turning it into a precise and strictly mathematical foundation for thermodynamics.